New stars are being born. Massive blazing giants that dwarf our sun are igniting for the first time in stellar nurseries scattered across the galaxy. These stellar infants are mere millions of years old, cosmic babies in a universe that is 13.8 billion years ancient. This shouldn't be possible. In a universe that has had nearly 14 billion years to age, every star should be ancient. The cosmic clock should have run down long ago, leaving behind only the cold, dim remnants of stellar death. Yet when we peer through our most powerful telescopes, we see young, hot, blue stars burning with the fierce intensity of cosmic youth. We thought we understood stellar lifespans. The most massive stars, the very ones we observe being born today, should burn through their nuclear fuel in just a few million years before exploding as supernova. In a universe billions of times older than these stars' lifespans, we should see only the fading embers of cosmic history. Instead, we see stellar nurseries actively creating new stars right now. But here's what makes this deeply unsettling. Not only are young stars still forming, but they're forming at rates that seem impossible given the age and supposed evolution of the universe. The Hubble Space Telescope and James Webb Space Telescope have revealed star formation occurring at distances so vast that we re-see galaxies, as they were when the universe was less than 1 billion years old. These ancient galaxies are churning out massive stars at rates far exceeding what modern theory predicted possible. The evidence is overwhelming and disturbing. The Large Magellanic Cloud, our cosmic neighbor, is currently experiencing one of the most intense periods of star formation in its history. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is a stellar maternity ward where hundreds of new stars are being born every million years. The Cygnus X region contains star-forming complexes so active they recreating stars with masses up to 100 times our sun. Tonight, we're going to uncover the cosmic machinery that keeps creating new stars in an ancient universe. We'll explore the hidden cycles of stellar death and rebirth that recycle cosmic material across billions of years. And we'll discover that the universe isn't winding down as we expected. It is actively maintaining itself through processes so violent and spectacular, they rewrite the laws of cosmic evolution. This isn't just about stars. This is about understanding whether the universe has a built-in mechanism for renewal, whether cosmic evolution is cyclical rather than linear, and whether the apparent youth of stellar populations challenges our fundamental understanding of cosmic time itself. Dr. Massimo Roberto from the Space Telescope Science Institute has spent decades studying star formation using the Hubble Space Telescope. His research has revealed that star formation is not just ongoing, but accelerating in certain regions of the universe. What we're rediscovering is that the universe is far more dynamic and self-renewing than we ever imagined. The cosmic timeline isn't a straight line from order to chaos. It is a complex cycle of destruction and rebirth that maintains stellar youth across cosmic time. The Spitzer Space Telescope, before its retirement in 2020, maps star formation throughout our galaxy using infrared light that penetrates cosmic dust. The mission revealed that our Milky Way is currently forming new stars at a rate of approximately 1 to 2 solar masses per year. This means that every year, the equivalent of 1 or 2 new suns ignites somewhere in our galaxy alone. Multiply this across the hundreds of billions of galaxies in the observable universe, and the numbers become staggering. Trillions of new stars are being born every year in a cosmos that should have exhausted its star-forming potential billions of years ago. But the mystery deepens when we consider stellar lifetimes. The most massive stars, those burning brightest in stellar nurseries, have lifespans measured in millions of years, a cosmic eye blink. These stars should have died and disappeared countless times over during the universe's 13.8 billion year history. Yet we see them everywhere, suggesting a continuous cycle of stellar birth that has maintained cosmic youth for nearly the entire age of the universe. The James Webb Space Telescope has revolutionized our understanding of early star formation by observing galaxies from when the universe was less than 500 million years old. These observations reveal that massive star formation began almost immediately in cosmic terms, suggesting that the processes creating young stars today have been operating since the universe's earliest epochs. Dr. Garth Illingworth from the University of California, Santa Cruz, leads observations of the most distant galaxies visible to JWST. His research reveals star formation rates in the early universe that challenge our models. We're seeing galaxies from the cosmic dawn that are forming stars at rates comparable to what we observe today. This suggests that the universe has been in a continuous state of stellar renewal from almost the very beginning. The contradiction becomes even more apparent when we consider the cosmic timeline. The universe began with the Big Bang 13.8 billion years ago. The first stars formed roughly 100 to 200 million years later. Those primordial stars were massive giants that should have died within a few million years. Yet somehow, star formation has continued unabated across cosmic time, maintaining populations of young, massive stars that shouldn't exist in an aging universe. Recent discoveries have revealed star formation occurring in environments previously thought to be too old or depleted to create new stars. Ancient globular clusters, some of the oldest objects in the universe, have been found to contain multiple generations of stars, including some that are surprisingly young relative to the cluster's formation time. The implications extend beyond simple stellar birth rates to challenge our understanding of cosmic evolution itself. If the universe can continuously renew itself through stellar formation, then the expected heat death, the eventual end state where all energy is dissipated and no new stars can form, might be far more distant than we calculated. This cosmic renewal process operates through mechanisms so complex and interconnected that they challenge our linear view of cosmic time. Stellar death triggers stellar birth. Galactic collisions spark star formation. Dark matter dynamics create the large-scale structure needed for ongoing stellar genesis. The universe reveals itself not as a dying system winding down, but as a self-sustaining cosmic ecosystem. If you're fascinated by cosmic mysteries that challenge our understanding of time itself, subscribe and hit thumbs up. And here is a question that might reshape how you think about cosmic evolution. If stars can be young in an ancient universe, what does that mean for the ultimate fate of the cosmos? Comment below. I'll pin the most thought-provoking answer. Over the next hour, we'll journey through the evidence for ongoing star formation, explore the cosmic mechanisms that enable stellar youth in an ancient universe, and discover that the cosmos operates according to principles far more dynamic and renewable than our everyday experience suggests. We'll find that the universe isn't simply aging. It is actively regenerating itself through cycles of stellar death and rebirth that have maintained cosmic vitality for nearly the entire age of creation. The young stars blazing in tonight's sky are not cosmic anomalies, but evidence of the universe as most fundamental property, its ability to renew itself across time spans that dwarf human comprehension. Now let's begin by understanding exactly what we mean by young and old in cosmic terms, and why the coexistence of both challenges everything we thought we knew about the universe's evolution. Chapter 1. Cosmic timescales. To understand why young stars in an ancient universe represent such a profound mystery, we must first grasp the almost incomprehensible scales of cosmic time and stellar evolution. The universe operates on timescales so vast they challenge human intuition. Yet within these cosmic epochs, stellar lifetimes vary by factors of millions, creating a complex hierarchy of cosmic ages that defies simple explanation. The universe began 13.8 billion years ago with the Big Bang, an event that created space, time, and all the matter and energy that would eventually form galaxies, stars, and planets. To put this cosmic age in perspective, If the entire history of the universe were compressed into a single year, human civilization would occupy only the last few seconds before midnight on December 31st. But stellar lifetimes operate on dramatically different scales depending on stellar mass. The smallest red dwarf stars burn so slowly they can exist for trillions of years, far longer than the current age of the universe. Our Sun, a medium-sized star, has a total lifetime of approximately 10 billion years and is currently middle-aged at 4.6 billion years. The most massive stars, however, live fast and die young, burning through their nuclear fuel in just a few million years. Dr. Virginia Trimble from the University of California, Irvine, has studied stellar evolution timescales throughout her career. Her research reveals the dramatic variation in stellar lifetimes. A star with 50 times the mass of the Sun will exhaust its nuclear fuel and explode as a supernova in just 3 to 5 million years. In cosmic terms, this is almost instantaneous. These stars are born and die faster than continents move on Earth. This creates the central paradox. If the universe is 13.8 billion years old, and the most massive stars live only a few million years, then any massive star we observe today must be extremely young relative to cosmic time. These stellar giants should have died and disappeared thousands of times over during the universe's history, yet we see them blazing brightly in stellar nurseries throughout the cosmos. The Orion Nebula, one of the most spectacular star-forming regions visible from Earth, contains dozens of massive stars that are less than 1 million years old. These stellar infants are surrounded by the same cloud of gas and dust from which they formed, their intense radiation and stellar winds still carving out cavities in their birth material. Dr. Mark Makorian from the European Space Agency has used the Hubble Space Telescope to study star formation in the Orion Nebula in unprecedented detail. His observations reveal that star formation is an ongoing process, with new protostars still condensing from the nebular material. We're witnessing stellar birth in real time. Some of the objects we observe in Orion are so young they haven't even finished contracting to their final stellar size. These are baby stars in the process of being born. But the mystery extends beyond individual star-forming regions to encompass the entire galaxy. The Milky Way contains an estimated 100 to 400 billion stars, ranging in age from nearly as old as the universe itself to stellar embryos currently forming in molecular clouds. This vast population represents multiple generations of stellar death and rebirth spanning cosmic history. The oldest stars in our galaxy are found in globular clusters and the galactic halo, ancient stellar populations that formed when the Milky Way was young and metal-poor. These stars contain almost no elements heavier than hydrogen and helium, marking them as relics from the universe's early epochs when heavier elements had not yet been manufactured in stellar cores. In contrast, the youngest stars form in the galaxy's spiral arms, where dense molecular clouds provide the raw material for ongoing stellar birth. These stellar nurseries contain gas enriched with heavy elements created by previous generations of stars, demonstrating that star formation is not a one-time event, but a continuous process that has operated throughout cosmic history. Dr. Bruce Elmgreen from IBM Research has studied the galactic distribution of star-forming regions using data from multiple space telescopes. His research reveals that star formation follows complex patterns related to galactic structure and dynamics. The spiral arms of the galaxy act like cosmic assembly lines for star formation. As gas clouds move through these regions, they're compressed and triggered to collapse into new stars, maintaining a continuous cycle of stellar birth. The timescale paradox becomes even more apparent when we consider stellar evolution in detail. Massive stars progress through their entire life cycle, from protostar to main sequence to red giant to supernova, in just a few million years. This means that in the 13.8 billion years since the Big Bang, There's been time for thousands of successive generations of massive stars to live and die. Yet we observe massive stars today that are essentially identical to those that would have existed billions of years ago, suggesting that the star formation process itself has remained remarkably constant across cosmic time. The physical laws governing stellar birth, evolution, and death have operated unchanged since the universe's earliest epochs. Computer simulations of cosmic evolution reveal that star formation rates have varied significantly throughout the universe's history. The peak era of star formation occurred when the universe was roughly 2 to 3 billion years old, during a period astronomers call cosmic noon. During this epoch, galaxies were forming stars at rates 10 to 100 times higher than what we observe today. Dr. Casey Popovich from Texas A&M University has studied star formation history using observations of distant galaxies. His research shows that the universe has experienced multiple periods of enhanced star formation. The cosmic star formation rate has not been constant. There have been boom and bust cycles, with some epochs producing far more massive stars than we see today. Yet even during the quiet periods, star formation has never completely stopped. This variable star formation history adds another layer to the young star mystery. If star formation rates were much higher in the past, then the current generation of young stars represents only the latest phase of a process that has been operating since cosmic dawn. The distribution of stellar ages within individual galaxies provides additional evidence for ongoing star formation. The Andromeda Galaxy, our nearest galactic neighbor, contains stellar populations ranging from nearly 13 billion years old to active star-forming regions, creating new stars today. This age spread demonstrates that galaxies maintain multi-generational stellar populations across cosmic time. Recent observations with the James Webb Space Telescope have pushed our view of star formation back to the universe's earliest epochs. JWST has detected galaxies forming stars when the universe was less than 500 million years old, revealing that the processes creating young stars today began operating almost immediately after the cosmic dark ages ended. Dr. Brant Robertson from the University of California, Santa Cruz, leads early universe observations with JWST. His research reveals that star formation began earlier and proceeded faster than predicted. We're seeing fully formed galaxies with active star formation at redshifts we did not expect to find them. This pushes back the timeline for when star formation began and suggests it has been a continuous process throughout cosmic history. The chemical evolution of the universe provides another perspective on stellar timescales. The first stars contained only hydrogen and helium created during the Big Bang. As these primordial stars died and expelled their processed material into space, they enriched the interstellar medium with heavier elements necessary for planet formation and complex chemistry. Each successive generation of stars formed from increasingly enriched material, creating the chemical complexity we observe in modern stellar populations. Young stars forming today contain elements forged in the cores of countless previous generations, demonstrating that star formation is intimately connected to the cosmic recycling of matter across billions of years. As we contemplate these vast cosmic timescales, we're forced to confront the fundamental question: how can processes operating on million-year timescales maintain stellar youth in a billion-year-old universe? The answer lies in understanding that the cosmos operates not as a simple linear progression from order to chaos, but as a complex, self-sustaining system capable of renewing itself across time spans that dwarf human comprehension. The coexistence of ancient and young stellar populations reveals that cosmic time itself is layered and cyclical, with processes operating simultaneously on vastly different scales. The universe maintains its youth not by stopping time, but by continuously recycling and renewing itself through mechanisms we're only beginning to understand. Chapter 2. Stellar Nurseries. Hidden within the vast emptiness of interstellar space, lie some of the most spectacular and creative regions in the universe. Stellar nurseries, where new stars are born from the collapse of molecular clouds in processes so violent they reshape entire sectors of galaxies. The Eagle Nebula, immortalized by the Hubble Space Telescope's famous Pillars of Creation image, exemplifies how stellar nurseries function. This star-forming region lies 7,000 light-years from Earth and currently hosts the birth of dozens of new stars within towering columns of gas and dust. The pillars themselves are being carved by the intense radiation and stellar winds from recently formed massive stars, creating a dynamic environment where stellar birth and stellar influence interact in complex feedback loops. Dr. Jeff Hester from Arizona State University led the Hubble observations that revealed the Eagle Nebula's intricate structure. His research demonstrates how stellar formation occurs through the gravitational collapse of dense molecular clouds. What we see in the Eagle Nebula is star formation caught in the act. Dense knots of gas within the pillars are collapsing under their own gravity to form protostars, while the radiation from nearby young stars is simultaneously evaporating the surrounding material. The process begins when molecular clouds, vast regions of cold gas and dust scattered throughout galaxies, become gravitationally unstable. These clouds can span hundreds of light years and contain enough material to form thousands of stars. When triggered by shock waves from supernova, galactic collisions, or simply their own gravitational evolution, these clouds fragment into smaller cores that collapse to form individual stars. The collapse process follows precise physical laws that have remained unchanged throughout cosmic history. As a gas cloud contracts under gravity, it heats up and begins to spin faster due to conservation of angular momentum. When the core temperature reaches approximately 10 million Kelvin, nuclear fusion ignites and a new star is born. But star formation is not a gentle process. The Cygnus X region, one of the most active star-forming complexes in our galaxy, demonstrates the violent nature of stellar birth. This region spans 600 light-years and contains enough gas to form millions of new stars. The intense ultraviolet radiation from young, massive stars creates vast bubbles of hot gas that compress surrounding material, triggering additional waves of star formation. Dr. Xavier Koenig from the Harvard-Smithsonian Center for Astrophysics has mapped star formation in Cygnus X using infrared observations that penetrate cosmic dust. His research reveals the complex interplay between stellar birth and stellar influence. Star formation is a self-propagating process. Young stars create conditions that trigger the formation of additional stars, creating chain reactions that can span thousands of light years and millions of years. The Spitzer Space Telescope, during its 16-year mission, revolutionized our understanding of stellar nurseries by observing them in infrared light that reveals warm dust and embedded protostars invisible to optical telescopes. Spitzer discovered that star formation occurs in virtually every galaxy, from massive ellipticals to small irregular systems, demonstrating that stellar nurseries represent a universal phenomenon. Recent observations have revealed that stellar nurseries are far more complex and dynamic than previously understood. The Atacama Large Millimeter Array (ALMA) radio telescope has provided unprecedented views of the earliest stages of star formation, revealing the detailed structure of collapsing gas cores and the formation of planetary systems around newborn stars. Dr. Crystal Brogan from the National Radio Astronomy Observatory uses ALMA to study protostellar evolution in nearby star-forming regions. Her observations reveal that star formation begins long before stars become visible. We can now observe the very earliest stages of stellar birth, when protostars are still embedded deep within their natal gas clouds. These observations show that star formation is a gradual process that unfolds over millions of years. The environmental conditions within stellar nurseries determine the types of stars that form. Regions with dense, massive gas clouds tend to produce more high-mass stars, while smaller, less dense clouds typically form lower mass stars like our Sun. This mass distribution follows a universal pattern called the initial mass function, which appears remarkably consistent across different galaxies and cosmic epochs. However, the efficiency of star formation varies dramatically between different environments. Only about 1 to 2% of the gas in a typical molecular cloud actually becomes incorporated into stars. The rest is either expelled by stellar winds and radiation or remains as diffuse interstellar material. This low efficiency explains why star formation can continue for billions of years without exhausting the available gas supply. The Rosette Nebula provides a spectacular example of how massive stars shape their birth environments. This nebula contains a central cavity carved out by the stellar winds and radiation from a cluster of young, hot stars. The intense energy from these stellar giants has blown away most of the original gas cloud, leaving behind a beautiful shell of glowing gas while simultaneously triggering star formation in the surrounding material. Dr. Robert Odell from Vanderbilt University has studied how stellar feedback affects star formation efficiency in numerous nebulae. His research shows that massive stars both destroy and create stellar nurseries. High-mass stars are cosmic vandals and architects simultaneously. They destroy their birth clouds through intense radiation and stellar winds, but they also compress nearby gas to trigger new episodes of star formation. The distribution of stellar nurseries throughout galaxies follows patterns related to galactic structure and dynamics. In spiral galaxies like the Milky Way, star formation occurs primarily in the spiral arms, where gas clouds are compressed by density waves. Elliptical galaxies typically show much lower rates of star formation due to their lack of cold gas, while irregular galaxies can have chaotic star formation patterns driven by galactic interactions. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, currently experiences one of the most intense periods of star formation in its history. The Tarantula Nebula within this galaxy contains some of the most massive stars known, including R136A1, which has an estimated mass of 265 times our Sun. This extreme star formation activity demonstrates that stellar nurseries can produce objects at the very limits of stellar physics. Dr. Paul Crowther from the University of Sheffield has studied the most massive stars in the Tarantula Nebula using ground-based and space telescopes. His research reveals that stellar nurseries can create stars far more massive than previously thought possible. The Tarantula Nebula is forming stars at the absolute extreme of what is physically possible. These monster stars push our understanding of stellar formation to its limits. The chemical composition of stellar nurseries has evolved over cosmic time as previous generations of stars have enriched the interstellar medium with heavy elements. Modern stellar nurseries contain elements like oxygen, carbon, and iron that were created in the cores of ancient stars, enabling the formation of rocky planets and complex molecules within protoplanetary disks. This chemical evolution creates a cosmic recycling process where the death of one generation of stars provides the raw material for the next generation. Supernova explosions scatter heavy elements throughout galaxies, while stellar winds from massive stars create bubbles of hot, enriched gas that eventually cools and condenses into new molecular clouds. The James Webb Space Telescope has revealed stellar nurseries in unprecedented detail, showing the formation of brown dwarfs, planetary systems, and exotic stellar objects that challenge our classification schemes. JWST observations of the Orion Nebula have revealed hundreds of previously unknown protostars and planetary disks, demonstrating that stellar formation is even more active and complex than previously realized. Dr. Klaus Pontoppidan from the Space Telescope Science Institute leads JWST observations of nearby star-forming regions. His research is revealing new aspects of stellar birth. JWST is showing us that stellar nurseries are incredibly rich and complex environments. We're finding objects that don't fit our traditional categories. Things that might be stars, might be planets, or might be something entirely new. The cosmic web of dark matter provides the underlying structure that enables stellar nurseries to form and persist over cosmic time. Dark matter halos create gravitational wells that concentrate normal matter into galaxies and star-forming regions. Without this dark matter scaffolding, the universe would lack the structure necessary for ongoing star formation. Computer simulations show that stellar nurseries are not isolated phenomena, but part of a cosmic ecosystem that includes galactic mergers, supermassive black holes, and intergalactic gas flows. This larger context explains how star formation can continue across cosmic time despite the apparent aging of the universe. As we explore these cosmic maternity wards, we discover that they represent one of the universe's most fundamental and enduring processes. Stellar nurseries have operated continuously for nearly 14 billion years, maintaining the cosmic cycle of stellar birth that keeps the universe young and vibrant despite its ancient age. Chapter 3: Galactic Recycling. The universe has discovered the secret of eternal youth through one of the most spectacular recycling programs in existence: the continuous transformation of stellar death into stellar birth across cosmic time. This galactic recycling process operates on scales so vast and through mechanisms so violent that they reshape entire regions of space, ensuring that new stars can continue forming in a universe billions of years old. Every massive star that dies in a supernova explosion becomes a cosmic recycling center, scattering elements forged in stellar cores across thousands of light years of space. These stellar deaths are not endings but beginnings, providing the enriched material necessary for the next generation of stars and enabling the chemical complexity that makes planets and life possible. The Orion Nebula in the constellation Cygnus exemplifies this cosmic recycling in action. This spectacular structure is the expanding shock wave from a supernova explosion that occurred roughly 8,000 years ago. The blast scattered stellar material across 110 light-years of space, creating a glowing shell of hot gas that continues to expand at speeds of 600 kilometers per second. Dr. William Blair from Johns Hopkins University has studied supernova remnants like the Orion Nebula using ultraviolet and optical telescopes. His research reveals how stellar explosions enrich the interstellar medium. When a massive star explodes as a supernova, it doesn't just destroy, it creates. The explosion synthesizes new elements and scatters them into space, where they become incorporated into the next generation of stars and planets. The physics of stellar recycling operates through multiple mechanisms that have remained consistent throughout cosmic history. Massive stars during their lifetimes expel material through stellar winds that can remove entire solar masses of material over millions of years. Red giant and asymptotic giant branch stars shed their outer layers in spectacular planetary nebulae, returning processed material to the interstellar medium. But the most dramatic recycling events occur during the final moments of stellar death. Type II supernova, caused by the core collapse of massive stars, release energies equivalent to 1,044 joules in just seconds. These explosions are so powerful, they can outshine entire galaxies and are visible across billions of light years of space. The Cassiopeia, a supernova remnant, provides a detailed case study of cosmic recycling in progress. This object, the expanding debris from a supernova explosion that occurred around 1680 CE, has been studied extensively by the Hubble Space Telescope, Spitzer Space Telescope, and Chandra X-ray Observatory. Dr. Dan Milosavljevic from Purdue University leads multi-wavelength studies of Cassiopeia. His research reveals the complex structure of supernova ejecta. CASE is like a cosmic laboratory, showing us how stellar explosions work. We can see how different elements were synthesized in the star S-core and how they being dispersed into space. The iron, silicon, and calcium we observe were literally forged in the heart of a dying star. The chemical enrichment process follows a cosmic timeline that spans the entire history of the universe. The first generation of stars, formed from primordial hydrogen and helium, contained no heavy elements. When these population 3 stars died, they began the enrichment process by scattering the first metals into space. Each subsequent generation of stars formed from increasingly enriched material, creating the chemical complexity we observe in modern stellar populations. Our Sun, a relatively young star at 4.6 billion years, contains elements from dozens of previous stellar generations, making it a cosmic archaeology site that preserves the chemical history of our galaxy. The local bubble, a region of hot, low-density gas surrounding our solar system, demonstrates galactic recycling on local scales. This cavity, roughly 300 light-years across, was carved out by supernova explosions from nearby massive stars over the past 10 to 15 million years. The bubble's hot interior contains gas heated to over 1,000,000 degrees Kelvin by these stellar explosions. Dr. Barry Welsh from the University of California, Berkeley, has mapped the local bubble structure using ultraviolet observations of nearby stars. His research reveals that our solar system sits within an active region of galactic recycling, we reliving inside a supernova-created cavity in space. The local bubble shows us that stellar recycling is not just a distant phenomenon. It's happening all around us and has shaped the environment of our solar system. Stellar winds from massive stars contribute significantly to galactic recycling between supernova events. Wolf-Rayet stars, which represent a late evolutionary phase for very massive stars, can lose several solar masses of material per million years through intense stellar winds. These winds create expanding bubbles of hot gas that sweep up and compress surrounding material. The Orion Nebula contains a central cavity created by stellar winds from a cluster of young massive stars. The intense radiation and particle streams from these stellar giants have excavated a region 50 light-years across, creating shock fronts that compress surrounding gas and trigger additional star formation. Computer simulations reveal that galactic recycling operates as a self-sustaining process. Stellar deaths create hot bubbles that merge to form larger structures called superbubbles. These expanding cavities can break through galactic disks, creating galactic fountains that transport enriched material into the galactic halo, before it eventually falls back to trigger new episodes of star formation. Dr. Dieter Breitschwart from the Vienna University of Technology has modeled galactic fountain flows using sophisticated computational techniques. His research shows that galactic recycling operates on multiple scales. Stellar feedback creates a complex circulation pattern within galaxies. Hot gas rises into the halo, cools, and falls back down to form new molecular clouds. This galactic breathing process has operated for billions of years. The antennae galaxies provide a spectacular example of galactic recycling triggered by galactic interactions. This pair of colliding galaxies, located 45 million light-years from Earth, shows intense star formation driven by the compression of gas clouds during the merger process. The collision has created numerous stellar nurseries where new stars form at RTEs far exceeding those in isolated galaxies. Simultaneously, the massive stars formed in this burst are dying in supernova, enriching the interstellar medium and triggering additional waves of star formation. Dr. Brad Whitmore from the Space Telescope Science Institute has studied star formation in the antennae galaxies using Hubble Space Telescope observations. His research reveals how galactic interactions enhance recycling. The antennae show us galactic recycling in overdrive. The collision is triggering intense star formation while simultaneously accelerating stellar death through supernova explosions. It's a cosmic feedback loop operating at galactic scales. Asymptotic giant branch, AGB, Stars represent another crucial component of galactic recycling. These evolved stars, with masses between 1 and 8 times our Sun, shed their outer layers through stellar winds over periods of thousands of years. The material they expel includes carbon and other elements synthesized during their lifetimes. The Cat's Eye Nebula exemplifies the beautiful and complex structures created by a GB stellar mass loss. This planetary nebula shows intricate knots, jets, and shells of gas expelled by the dying central star. The nebula's complex structure reveals that stellar mass loss is not a simple, steady process but involves episodic ejections and interactions with previously expelled material. The efficiency of galactic recycling varies between different types of galaxies. Spiral galaxies like the Milky Way maintain active recycling through ongoing star formation and stellar death. Elliptical galaxies, which formed most of their stars early in cosmic history, show less active recycling and gradually fade as their stellar populations age. Dwarf irregular galaxies often show bursts of star formation triggered by interactions with larger galaxies. These starburst episodes can consume significant fractions of a galaxy's gas supply while simultaneously enriching the interstellar medium through rapid stellar evolution. Recent observations with the James Webb Space Telescope have revealed galactic recycling operating in the early universe when galaxies were young and gas-rich. JWST observations show that even the earliest galaxies were already enriching their interstellar media through stellar death and recycling. Dr. Roberto Maialino from the University of Cambridge uses JWST to study chemical evolution in distant galaxies. His observations revealed that galactic recycling began early in cosmic history. We are seeing evidence for stellar recycling in galaxies that formed when the universe was less than 1 billion years old. This shows that the processes maintaining stellar youth have operated throughout cosmic time. The cosmic recycling process extends beyond individual galaxies through mechanisms like galactic winds and cosmic ray transport. Material expelled from one galaxy can travel through intergalactic space and contribute to star formation in neighboring systems, creating a cosmic web of recycling that operates on the largest scales. As we trace the pathways of galactic recycling, we discovered that the universe has created a self-sustaining system capable of maintaining stellar youth across cosmic time. The death of massive stars provides the raw material for new stellar generations, while the energy from stellar explosions creates the conditions necessary for continued star formation. This cosmic recycling program operates with an efficiency that ensures the universe can continue forming new stars for trillions of years into the future, despite having already consumed significant fractions of its original hydrogen fuel. The secret lies in the continuous processing and reprocessing of cosmic material through cycles of stellar birth, life, and death. Chapter 4. Stellar Generations. The universe maintains its stellar youth through a vast cosmic relay race where each generation of stars passes enriched material to the next, creating an unbroken chain of stellar evolution that has operated for nearly 14 billion years. This multi-generational process reveals that what we call young stars are actually the latest participants in a cosmic dynasty that stretches back to the universe's earliest epochs. The concept of stellar generations revolutionized astronomy when scientists realized that stars could be classified not just by their current properties, but by the chemical heritage passed down from their stellar ancestors. This cosmic genealogy reveals the universe's evolutionary history, written in the chemical composition of stellar atmospheres. Population 3 stars represent the universe's firstborn stellar generation, forming roughly 100 to 200 million years after the Big Bang from gas clouds containing only hydrogen and helium created during primordial nucleosynthesis. These primordial giants were among the most massive stars ever to exist, with masses potentially reaching 1,000 times our Sun's mass. Dr. Volker Braun from the University of Texas at Austin has spent his career modeling the formation and evolution of population 3 stars using sophisticated computer simulations. His research reveals the unique characteristics of the universe's first stellar generation. Population 3 stars were fundamentally different from any stars we see today. Without heavy elements to cool their forming gas clouds, they grew to enormous masses and burned incredibly hot. When they died in spectacular supernova, they began the cosmic process of chemical enrichment. These primordial stars lived fast and died young, with lifetimes measured in just a few million years. But their deaths were transformative events that changed the chemical composition of the entire universe. Their supernova explosions synthesized and scattered the first heavy elements, carbon, oxygen, nitrogen, silicon, and iron, into the pristine hydrogen-helium cosmos. The Hubble Space Telescope and James Webb Space Telescope have searched for direct evidence of population 3 stars, but have not yet definitively detected any surviving examples. This absence itself tells a story. These massive primordial stars burned so briefly that none survive today, over 13 billion years later. However, their chemical signatures persist in the oldest stars we can observe. Population 2 stars, which formed from gas clouds enriched by the first generation of stellar deaths, show heavy element abundances thousands of times lower than modern stars. These ancient stellar fossils preserve evidence of the universe's early chemical evolution. Dr. Anna Frebel from MIT leads the search for the most metal-poor stars in the Milky Way galaxy. Her observations using ground-based telescopes reveal stars that formed very early in cosmic history. When we find a star with incredibly low heavy element abundance, we're looking at something that formed from gas enriched by only one or a few population 3 supernova. These stars are fossil records of the universe's earliest chemical enrichment. The globular cluster N92 contains some of the oldest known stars in our galaxy, with ages approaching 13 billion years. These ancient stellar populations show the chemical signatures of early stellar generations, with heavy element abundances roughly 250 times lower than our Sun. Yet even these primordial stellar communities show evidence for multiple generations of chemical enrichment. Population I stars, which include our Sun and most visible stars in the galaxy today, formed from material enriched by billions of years of stellar nucleosynthesis. These modern stars contain heavy elements comprising roughly 2% of their mass, providing the chemical complexity necessary for planet formation and life. But here's what makes stellar generations remarkable. The process hasn't stopped. New generations of stars continue forming today from material enriched by the deaths of previous generations. The Orion Nebula, one of the nearest star-forming regions, is currently creating population I stars from gas clouds enriched by countless previous stellar cycles. The stellar initial mass function reveals how each generation distributes stellar masses, with most stars forming as small, long-lived red dwarfs, while only a small fraction become massive, short-lived giants. This distribution ensures that each stellar generation includes both stars that die quickly, to enrich the interstellar medium, and stars that live long enough to witness multiple subsequent generations. Dr. Pavel Krupa from the University of Bonn has studied the stellar mass function across different environments and cosmic epochs. His research reveals remarkable consistency in how stellar generations form. The way stars distribute their masses has been remarkably constant throughout cosmic history. Each generation forms mostly small stars with a few giants, ensuring both long-term stellar survival and rapid chemical enrichment. The chemical evolution of stellar generations follows predictable patterns that allow astronomers to trace galactic history. Elements like oxygen and magnesium, produced primarily by massive stars, increase rapidly in early stellar generations. Iron, produced mainly by Type Ia supernova from intermediate mass stars, increases more gradually over cosmic time. This chemical archaeology reveals that the Milky Way's stellar populations formed through multiple phases of chemical enrichment. The galactic halo contains ancient metal-poor stars from early epochs, while the galactic disk contains younger, metal-rich stars formed more recently. The Large Magellanic Cloud provides a detailed case study of stellar generations in progress. This satellite galaxy contains stellar populations spanning nearly its entire 10 billion-year history, from ancient globular clusters to active star-forming regions creating new stars today. Dr. Knut Olsen from the National Optical Infrared Astronomy Research Laboratory has mapped stellar generations in the Large Magellanic Cloud using surveys that observe millions of individual stars. His research reveals ongoing stellar generation cycles. The LMC is like a cosmic laboratory showing us how stellar generations evolve over time. We can see ancient stellar populations alongside regions actively forming the next generation of stars. Recent discoveries have revealed that stellar generations can overlap and interact in complex ways. The Omega Centauri globular cluster, long thought to contain a single stellar generation, actually hosts multiple generations of stars with different ages and chemical compositions. These multi-generational stellar clusters form through processes where early stellar generations enrich the cluster environment, enabling subsequent waves of star formation from the chemically enriched material. The result is stellar communities that span hundreds of millions of years of formation history. Computer simulations of galactic chemical evolution reveal how stellar generations shape the large-scale properties of galaxies. Early generations of massive stars create galactic winds that can expel gas from small galaxies, while later generations form in the chemically enriched material that eventually falls back through galactic fountains. Dr. Joss Bland Hawthorne from the University of Sydney has modeled chemical evolution in galaxies similar to the Milky Way. His simulations show how stellar generations create chemical gradients across galactic disks. Each stellar generation leaves its chemical fingerprint in the interstellar medium. By modeling these chemical signatures, we can reconstruct the entire history of star formation in a galaxy. The discovery of hypervelocity stars has revealed that stellar generations can be disrupted and scattered across cosmic distances. These stars, ejected from the galactic center at speeds exceeding galactic escape velocity, carry the chemical signatures of their birth generations into intergalactic space. Brown dwarf observations have extended our understanding of stellar generations to include failed stars that never achieved nuclear fusion. These objects, with masses below the hydrogen-burning threshold, preserve the chemical composition of their birth material for billions of years, serving as fossil records of stellar generation chemistry. The James Webb Space Telescope has revolutionized studies of stellar generations by enabling observations of individual stars in distant galaxies. JWST can resolve stellar populations in galaxies millions of light-years away, revealing how stellar generations evolve in different galactic environments. Dr. Martha Boyer from the Space Telescope Science Institute uses JWST to study stellar populations in nearby galaxies. Her observations reveal the diversity of stellar generation histories. JWST is showing us that every galaxy has its own unique stellar generation story. Some galaxies formed most of their stars early and then stopped, while others have continued forming new generations throughout cosmic time. The concept of stellar generations reveals that the universe's ability to maintain stellar youth depends not on preventing aging, but on continuously creating new generations of stars from the enriched remains of previous generations. This multi-generational process ensures that fresh stellar populations can continue forming even as the universe itself ages. The chemical legacy passed between stellar generations creates an unbroken chain of cosmic evolution that connects the first stars to form after the Big Bang with the stellar nurseries operating today. Each new generation builds upon the achievements of its predecessors, creating increasing chemical complexity that enables new types of stellar systems and planetary environments. As we trace the genealogy of stellar generations, we discover that the universe operates like a vast cosmic family where the death of stellar ancestors enables the birth of stellar descendants, maintaining stellar youth through an endless cycle of cosmic renewal that has operated since the universe's earliest epochs.